I drew it linear, but I know that this molecule is not linear. Yes, sir?
How do we differentiate between bent like that and bent
All
like
right,
that?
we'll talk about that.
Okay.
What is the angle? This one was a 120-degree angle. See that? 120. This one is bent.
118.
Something happens when one of our orbitals is occupied by a lone pair, not a bonding pair of electrons. What happened then?
118.
They spread out. Listen, when you have these electrons that are making bonds, they are very localized. They're a very specific place. They've got to be in between those two because both atoms are sharing the electrons. However, when this central atom has a lone pair, that lone pair is not confined to a certain place. It spreads out some. Oh, that's me. Okay, sorry about that. Yeah. Okay, all right. So, as the lone pair is present and spreads out, it causes these bonds to get squeezed some because of this thing spreading out. And this spreads out and repels these and pushes them a bit and squeezes them. What's the rule, Nick? Say it loud so the camera can hear you. No, not by percents. It's about 2 degrees. We get a squeeze of about 2 degrees. There you go. Nick, be a star. What? They were 120 before. So squeezed by about 2 degrees, what is it now?
118.
It's 118. Yeah. Were you saying 138? All right, now I did have a note about this on the next slide where we have a coordination number of 4, but you'll hear it again too. The general rule is this. When you have a lone pair on there, that lone pair spreads out. That spreading out repels these to squeeze together a little bit more, about 2 degrees for each lone pair. So where this was 120, this one, let's see, there it is. Now we have a lone pair up here, squashing those together. Not much, I mean I'm making it a little bit exaggerated the way I describe it, but just know that these get squeezed a little bit. 118. Yes?
Don't the valence shell electrons still like fly around though?
We think that bonding electrons are specific to in between.
But then the valence shell, the lone pairs, do they also like stay in one
They
place?
stay in the, yeah. These are now hybridized orbitals.
Oh, so they're just
And
going
so
around.
yeah,
around
they're not normal P's, they're hybridized. And so yeah,
Okay.
you've got this big lobe up here that has the electrons in it.
Okay.
Yep. Okay, this, I don't think I have another 3. No. So we've done coordination numbers 2 and 3. We only have to go up to 6, so we're just moving right along. Don't fall asleep. All right, so now we're going to coordination number of 4. These dot structures are so easy, let's just not even talk about them. CH4, you know what CH4 looks like. CH4 was the first molecule we talked about in this class. I know we talked about CH4 on September 6th.
Wow.
September 6th, 2014. When it all started.
That was so last year.
And
That
we're all
was
about
so
to
last year, yes it was.
Get him.
Okay,
Make him
so
mad.
if we want to describe what the shape of that molecule is,
I think it's
let's see if I can take a guess.
Oh no, I really don't think it's like.
Oh no.
This is drawn like this.
Sorry.
The electrons we think, I can't get rid of that little arrow. The electrons we think are spreading out as far as they can get according to Vesper theory. Shouldn't the electrons then, or shouldn't the molecule look like this?
No, you can make it bigger.
No.
When you see
Yeah,
it
you can make the
on a flat
angle
surface, it
bigger.
looks like there's as far apart as they can get at 90 degrees. However, atoms and molecules don't think in 90 degree flat surface, they think 3 dimensions. So we can get these things to open up and have a little bit more than 90 degrees between them, like that. If, and I'm depending on my artistic savvy, which is non-existent.
Don't say that, Mr. Moore. We all think you're just.
Oh no, you know.
That
Yeah,
coffee
you
cup
saw how
color.
proud I was when I coffee cup calorimeter. All right, so this is approximately what it looks like. I rate that 10 out of 10.
Are you gonna start crying
You
now?
can still set up for the APR.
Okay. You'd hear Mrs. Kelly laughing from your house if I went. Is it Miss Tuba?
Who?
They both?
Yeah.
Wait,
They're
Mr.
great. I love
Tuba.
our art teachers.
Mrs. Tuba.
Mrs. Tuba.
She's one of the
Oh.
one of the art teachers. Okay, so this is the shape. Now these are no longer they're no longer 90-degree angles, but in 3 dimensions they can spread out more and occupy that entire spherical volume. What's the angle? 109.5. 109.5. That's what you said, Nabil, right?
I said 108.
Oh, you said it.
Hey, fight to.
You said that last year.
I said it once last year. I said it during our.
Not how. What is the name of that shape? You imagine these peripheral atoms being connected. You'd get a triangle from that one, and then the bottom one. They're all the exact same. If I turn this thing, if I did it right, you'd always have the central atom with 3 bonds going down and out, and then 1 going straight up. And then you turn it, 3 down and out, 1 straight up like that. So this is a very symmetrical molecule. 3-dimensionally symmetrical.
You wouldn't even know it.
In orgo? The 4 prefix in orgo was but, not tetra. What was there?
Isn't that quaternary?
Oh, when we name compounds, like CCl4 is carbon tetrachloride.
Oh, what are you doing?
And then
Okay.
the thing that you get your milk in is called a Tetra Pak. I don't know why it's called that though.
The milk cartons.
Yeah.
What are you doing?
Four
Stop,
sides,
bro.
maybe.
Stop. Don't be a mom, okay?
So anyway,
Don't be a mom. He did that everything. Don't be a
I'm
mom.
going to interrupt my class, Jude.
They're like doing something weird.
Okay, so anyway, that is the standard coordination number of 4. Now our central atom has 4 things around it. The NH3 molecule is our next coordination number of 4, and NH3 is going to have the lone pair on the end, which counts toward the coordination number. This has a coordination number of 4. It's going to be the same shape as this, except one of our orbitals is going to be a lone pair. I'm just going to take it right out. So now, what we have, you may remember this one too. You have a central atom. You have a lone pair up at the top, pushing down on these, which causes them to not flatten out, but they stay with this lone pair, or with the central atom up, and then the other is going down. What is this shape called?
Trigonal pyramid.
Trigonal
Pyramid. Right. Now, it's going to, yeah. All right, now pyramidal is actually correct. Not just pyramid. I always just call it pyramid.
A triangle
A
pyramid.
couple things about the name. See how this is tetrahedral? That's an adverb. It's describing a shape. This is called pyramidal, officially.
Trigonal pyramid.
For you.
I didn't know this was English class.
All right, now one other thing. This thing is more specifically called a trigonal pyramid, or pyramidal, not just the pyramid, because it's going to turn out later on we're going to see that there's a square pyramid. So we should be able to differentiate between those two. Yep. So this thing would be officially a trigonal
No, he didn't be in the class. It's pyramid, not pyramid dome.
No, it's more correct to do this. Oh. We can consult the authorities, Dr. Zundal, and they'll say pyramidal.
I don't memorize the book like it's
I remember the book.
He sleeps with the book.
I have like 5 books like
It's
this.
disrespectful. So there's our trigonal pyramid, right there. Okay, my friends, what is the bond angle for the ammonia molecule?
107.5.
Right, but we normally just say 107. It is a little bit more than 2 degrees. Call it 107.
Is there one? I thought there was a 105.
No.
Is there a 105? Okay. I'll leave that as
107.5 I can live with. the readers of the AP exam, they'll like to see that it's not 109.5. They don't want to see you write this. They want you to recognize. In fact, I have seen on free response sections of the AP exam questions that will have, what is the angle of the bonds in ammonia, and why is it not 109.5?
The lone pair is squishy.
On the AP exam, that question is there. So what would you say? Because that lone pair spreads out more than a bonding pair of electrons, and it repels the remaining bonds more. There's a little bit more repulsion. Or you could even say, as unscientific as, it squeezes the remaining. I'm sorry, guys. All right. Are we good with that one?
No, we're not.
Mr. Moore, aren't you so surprised that Lena didn't make some kind of like German joke or like George W. Bush joke about like the valence shell electrons taking too
I've
much
learned to not be
weight?
surprised about that.
No, think of some joke right now.
No, George W. Bush. Like taking up too much space.
The only president who took up too much space is Taft.
I don't even know who that is.
Oh yeah, because it's so.
You are?
You invite me, send me an invite.
It's funny. It was the
All right, we're moving on. Now the next compound, we're still in coordination number 4. We're not done yet. We've seen where your central atom has no lone pairs. Now the central atom has one lone pair in the ammonia molecule. The next one is our familiar water molecule, 2 lone pairs on the central atom.
Yeah.
Yes.
I know it's bent, but
Okay. Now we have my distorted pyramid. We now have 2 lone pairs on the central atom. I'll put the H's on so you can see it better. And that's causing the molecule to have the same. So we have a lone pair right here. In fact, I'll put the toothpicks in there. So that lone pair and that lone pair are repelling the other 2, causing them to not straighten out into a line, but it's got to be bent like this. This is your question you asked on the very first one.
Yeah.
How do you differentiate this bent from the other bent? You don't. You call them both bent, but the angle's not the same, is it? What's the angle of this one, Prox? This is our 105.
I knew there was a.
You knew there was. That's it. Now, because there's another lone pair, we get another approximately 2 degree squeeze. Yes, ma'am?
Can we say 105.5?
Yes.
Is it 104.5?
Sounds like a radio station.
Mr. Moore, I realized you got a new hula shirt.
Could we round you 60 to like 100?
I shoot you ruined the joke.
What?
That,
Wait, you didn't do it.
that was a great joke until you
No,
ruined
no,
it.
I don't even want 105.
You did it again. That was like, you were like. Yes.
I don't get.
All right. Any other questions that don't involve dancing?
Yeah, with does it make a difference? Is it more politically correct to draw the H side right next to the other H, or does it really not matter?
What are you doing?
When you draw the dot structure, draw it however you want. But you need to be able to, in your mind, visualize what the shape is, and it may not be reflected by what your dot structure. If you draw the H-O-H straight across from the other one, it's fine.
Okay.
Totally.
About this time.
What?
About this time.
No, it's funny to stop them.
If you insist.
Yay!
Nope, you're not invited.
Oh, wait.
All right.
So, why
Oops.
Rebate.
Yes, the tetrahedral angle is 109.5. It's like 109.47, very close to 109.5. So that's what has been the accepted angle that we all call the tetrahedral angle. No, nobody calls it 110. Nobody calls it 109. We call it 109.5. We got to follow the rules. There are other people in chemistry that came before us. They made the rules, and we have to follow them. Now, when you grow up and you're the authorities on chemistry, you can change things. But until then, we got to play by their rules.